Welcome to today's Explainer. We are jumping right into a super fascinating everyday engineering puzzle. How in the world do we safely bridge the gap between tiny, low-voltage prototypes and massive, high-voltage, real-world machines? It's a huge challenge, so let's get right into it.
Okay, let's dive into this. The source material captures the incredibly fast pace of a modern makerspace perfectly, with a quote that basically translates to, "Every day, new electronic projects are built here." And that really hits the nail on the head. Rapid prototyping is the absolute norm right now. We're talking about an environment where wild ideas move relentlessly from the drawing board straight to physical testing. And when you're iterating at that kind of breakneck speed day in and day out, you absolutely have to have reliable, repeatable ways to handle the electrical loads you're throwing around.
So in these rapid-fire daily tests, the workflow usually revolves around hooking up standard components, things like your basic motors and lights. Now, in the grand scheme of hardware development, these represent the low-power logic side of the equation. We're talking about tiny 5-volt or 12-volt signals coming straight from a microcontroller. Think of these standard components as the triggers. They let engineers figure out the baseline logic and functionality of a circuit before taking that exact same circuit and asking it to command, well, much larger and much heavier forces.
And this brilliantly illustrates the real problem. Let's slow down for a second, because this is where the stakes get high. As a project scales up, you hit a massive engineering roadblock. On one hand, you have your low-power testing, microcontrollers sipping mere milliamps of juice. But on the other hand, you have high-power machines pulling massive amps to do the actual heavy lifting. Obviously, you can't just wire a sensitive, delicate logic board directly to a giant industrial motor. If you try to cross those streams without proper isolation, boom, you're going to instantly fry the microchip and create a totally hazardous situation. That gap between low-power thinking and high-power doing, it absolutely has to be safely bridged.
Well, that brings us to the ultimate bridge, the true workhorse of safe control, the 12-volt relay. Honestly, this is where the engineering gets so elegant. A relay solves this whole scaling nightmare by using a super safe, low-power 12-volt signal from your logic board to energize a tiny little electromagnetic coil hidden inside. When that coil activates, it generates a magnetic field that physically pulls a totally separate, much heavier switch closed on the high-power side. The brilliant part here is a concept called galvanic isolation. Actually, scratch the technical jargon. It basically just means the low-voltage logic side and the high-voltage load side literally never touch electrically. That physical separation is the whole secret. It's exactly how a tiny microcontroller can safely boss around massive industrial power without risking the whole shebang.
So, the crucial point is, how do we safely control all of this power? That mechanical elegance of the 12-volt relay is the universal answer. It's the secret sauce that lets modern electronics scale up safely from a messy desk breadboard all the way to a heavy-duty factory floor. It gives us that vital isolation to turn a delicate prototype into an absolute powerhouse. But it leaves us with kind of a fascinating cliffhanger. Because as our systems get faster and faster, and those switch cycles reach into the millions, mechanical parts are eventually going to wear out. They just do. So at what point do the physical limits of a traditional clicking mechanical relay force us to evolve? Are solid-state relays the mandatory next step in safe control? Thanks for joining me for this explainer, and definitely keep exploring the mechanics behind the tech.